All right. Yeah, thank you very much for the introduction. Now, I've been asked at the conference, is that yet another of these boring talks that show that, okay, Tor is not perfect. Tor offers anonymity, but let's just see some details and how the anonymity is not as good as we would like to have it as theoretical researchers. Well, you can certainly look at the paper and look at this paper as a very good example of that category, because we, of course, show lots of results, actually more than I can present in this talk. And they show that Tor, as well as other variants of Tor, are not perfect. Okay, we knew that, but let's not really focus too much on that. All right, everyone knows Tor. You select nodes, stuff happens. I'm not going to go into detail here. The only reason I don't draw it as a black box is that the selection of these nodes is mainly the focus of this talk. All right, so we want to analyze Tor and the path selection strategies for Tor, namely the possibilities or the probabilities for these nodes E, B, and C to be chosen. And you want to look at how that influences adversarial success. Now, Alice sends messages, and for the talk, I'm just going to say, we want to say Alice sending a message to Bob should be indistinguishable from Alice sending a message to Charlie. It should be indistinguishable no matter, depending on how we select these nodes, and we're going to look at different strategies. I'm going to go into slight detail of them later. And we want them to be indistinguishable for a variety of adversaries that might control a group of Tor nodes that we specify via different metrics. For example, just a number of nodes, or any number of nodes as long as the combined bandwidth of the nodes is smaller than something, or any other such metric. Okay. Sorry for the definition here. We're going to use the ANOR definition of recipient anonymity. Also, we have sender and relationship anonymity in the paper. And it works as follows. It's kind of like a crypto game. Imagine like your int CPA game in encryption. We have an adversary. The adversary can compromise some Tor nodes in the beginning to set up the game, and then can control all Tor users. Can say, okay, now Alice, you send exactly this message to Bob. And Eve, you send a message to Charlie, and so on and so on. It can make some observations via the compromised nodes, and it can learn something and repeat the process and go on and on and on. At some point, it sends some challenge message. Now, that's where the dependency or the relation to the crypto games comes into play, because the challenger actually has some challenge bit B that the adversary doesn't know. And depending on this challenge bit, the observations the adversary is going to make or can potentially make are different, because if the bit is 0, then Bob actually sends a message. If it's 1, Charlie sends a message, right? This is the anonymity definition that we're going to use. And now we're going to try to show some cool things. Since this is kind of an advertisement talk, because we don't have much time to go into detail, I'll just talk a little bit about comparisons of what we're doing better than stuff we did before. The adversary, of course, has to guess the challenge bit, right? I guess you guys assumed that already. Now, there was already work at CCS14 against an adversary, or for an adversary that has at most k nodes for some number k, and for Tor's path selection algorithm back then, you input the Tor consensus, you say what k is, then it runs for a very short time and outputs some guarantees that are a little bit over-approximated. Okay, cool. So what can we do better? We give it a new name. We put a 2.0 there, for example. And now if you want to have different adversaries, you can just say, okay, well, cool, let's choose adversaries. Yeah, let's choose an adversary with a total bandwidth. Let's choose an adversary that has all nodes in Germany. Let's choose an adversary that has, maybe the most controversial one, a monthly budget of some number to rent Tor servers, which would mean it, of course, compromises existing servers, but has to pay for them, has to pay for their upkeep. Right? So we can try to measure the strength of this adversary as well. Then we can say, okay, let's compare Tor's path selection algorithm with, I don't know, something like uniform routing. Every Tor node has the same probabilities. That means performance is absolutely shitty. No one wants to use Tor anymore, but people are interested in analyzing that, so let's analyze that. Then there's a path selection algorithm that we proposed for CCS. We can also use that and have a look at that. We can have a look at something like LastTor that tries to base the paths that you take on your geographical location such that you don't go twice over the globe with high probability. And we can just choose these things, then input a consensus, then it runs for slightly longer time and outputs some results and some guarantees. Okay, that's kind of the goal. That's what we're doing. And now I'm going to bore you with some technical details in the hope that you can maybe learn something about how to analyze systems like Tor. Not just Tor, I think that applies to many things. So what we did is the following. We first simplified the analysis a lot. I'm not going to go into details here, but using some assumptions, for example, our adversary is passive, our adversary cannot adaptively choose nodes to kind of follow to the user, and doing some proofs, we said, okay, if we consider one Tor circuit at a time for the very small guarantees that we want to have here, that are one-shot guarantees, considering one Tor circuit at a time suffices. Okay. Now we said, okay, what can the adversary actually see? Let's assume the crypto is okay. Let's assume that there's no additional side channels the adversary can abuse. Then still an adversary can make observations of the entities that are in a Tor circuit. And we specify that as a 5-tuple. Okay, how does it look like? Well, this is Alice. Alice wants to talk to Bob. She chooses some guards. And let's just assume that Alice's internet service provider is malicious. So it can for sure see Alice, of course, and the guard. So from the perspective of Alice's internet service provider, even without doing any packet inspection or anything, that's definitely something it can see, right? So our observation would say, well, okay, there's Alice, there's this specific guard node, and some stuff I can't see. We have some special symbols for things I can't see. All right. If instead the middle node of a circuit is compromised, it can, of course, see both entry and guard. Can't see the sender and recipient. This would be the observation. All right. If guard and exit are compromised, well, we are not very lucky, but they can see everything. So the observation is comprised of everything that is connected to this Tor circuit. All right. What do we do then? We say for every such observation, for every 5-tuple there is, if this 5-tuple is more likely if the bit is 0 than if the bit is 1, that's bad, right? Because that means the adversary can learn something from the 5-tuple. Even if it cannot completely and immediately break anonymity, it can infer information about the recipient, just because the probabilities are different. So if we just for a second assume that we know which nodes are compromised, then we can, for every single node, for every single observation, calculate the probability that this particular set of nodes, compromised nodes, makes this observation if the challenge bit is 0, so if Alice sends a message to Bob. Right? We can do the same for a challenge bit being 1. And then we can compare these probabilities. We can say, well, okay, this is the impact of that one particular observation. Right? We can do that for every single observation. We can sum up the impacts and get the advantage the adversary has in distinguishing the challenge bit, in winning the game. Right? Okay, that's very cool. We would be done. But unfortunately, we don't know which nodes the adversary wants to compromise. We could check every subset, which in practice takes a little long. So we said, okay, let's over-approximate that here. Let's just say we find out the impact of each and every single Tor node, and we magically assign impacts of Tor nodes. If we have that, we can rank them, and we can find out which are the weakest points the adversary can attack to get the maximal advantage. Okay, how do we do that? Well, we go over every possible observation. Then we say, okay, who actually can make this observation? An observation of this form can be made exactly if the middle node is compromised. If additionally the guard was compromised, the observation would include the sender as well, right? So we can say, okay, this is made by the middle node. We calculate the impact of this small observation, and we just attach it to the middle node. We do that over every possible observation, and in the end, we get for every node some small impact value, how much this node impacted the observation advantages that the adversary could have. You still with me? Okay. I just assume that your silence means yes, and continue. So now we have for every node some small tag. Of course, in some cases it's more complicated. Please have a look at the paper for that. And now we say, okay, how can we get all these different types of adversaries we're interested in? We do that by saying, well, in addition to the advantage you have for a node, or this impact, we attach a cost to every node, some cost f. We have a function that gives each node a cost. And now the adversary has a budget. And if it wants to compromise node B, Well, we deduct that cost from the budget. And we do so for every node it wants to compromise. That's how an adversary can win, and that's how we measure adversaries. What we do then is we try to find the maximal set that is still satisfying this budget, and then we just sum over the advantages of the nodes in this set. And I just claim that this can be easily, or more easily approximated than considering every possible set. All right. Now, since this is advertisement anyway, please have a look at the paper for the slightly more complex formula at how actually we do things, because it's actually, you actually have to take care of a couple of very interesting side conditions. And also have a look at the technical report for the very exciting 17 pages of proof that are interesting because the adversary can learn stuff if he does not make observations. Right? That is something we also have to capture that made the proof kind of complicated. If the adversary has a slightly lower probability of not seeing something, then of course that also helps in figuring out who the recipient of a message is. Okay, now we've done that. We don't have much time left. We can look at graphs. There's graphs. This is graphs for Tor. This is graphs for comparing Tor with other path selection algorithms. Let's just look at a couple of small examples for that. This is again recipient anonymity. And we see here a comparison of the uniform path selection algorithm with Tor's path selection algorithm. Selector, that's an add-on that just restricts, allows you to restrict yourself to a specific exit node country. Then distributor, our thing, and two variants of last Tor, one where the recipients are close by, one where they are further away. And what you see here is, in layman terms, if it's below 0, that means they performed better than Tor against these adversaries. If it's above 0, it performed worse against Tor. So the adversary had a better chance of winning. And we can see that for k-node adversaries, something like uniform distribution is of course optimal, right? The adversary has a fixed number of nodes, and if you choose uniformly, of course the adversary has a smaller chance of winning. Similar for last Tor, because the variants we used were within clusters kind of uniform. If we're talking about bandwidth, it's a completely different picture, right? And then we can analyze the countries and how much impact countries have. What we can see here is that the US, if you only chose exit nodes from the US, kind of wins. That was expected. And you can also see some other cool correlations, some other cool things. You can see what happens if the adversary has a monetary budget. You can now finally compare these path selection algorithms to Tor's path selection algorithms and to each other. That's very cool. Okay, one thing I want to say before I have to shut up is the transition phase. Imagine the following scenario. Alice comes and says, hey, cool, look, there's this great new path selection algorithm. I'm totally going to use that. I'm going to be much more secure. And Bob is like, I don't know, Alice. Hey, sure, it's new. We didn't test it. I'm going to stick to the standard for now. And what happens here is that now these two users become easily distinguishable because the path selection algorithms, if they are different in the way they choose nodes, this is going to show. The adversary is going to notice these differences in probabilities. In graphs, we see values are pretty high. I think that's all the time I have for going into detail here. And we can also analyze stuff over time. We can just take several Tor consensuses and look how graphs change over time. It's also very cool. That's basically the stuff we can do with these tools. As a wrap-up, it's great, it's cool. Matter is something you should remember. For known adversaries, we can precisely calculate things, which is very cool. Then another takeaway message is, if you want to improve anonymity, that highly depends on against whom. If you want to improve anonymity against adversaries that have a certain small number of nodes, try to be uniform probably. If you want to improve anonymity against adversaries that have a certain amount of bandwidth, well, Tor is doing pretty good in that because the higher the bandwidth of a Tor node, the higher the probability that it's used. So the adversary can't exploit some differences here to get more than it can pay for. So you really have to look carefully. And another thing you could take away is, if you want to analyze anonymity, try to look at all possible things the adversary can see. Try to define it very carefully and look at the different probabilities of observations and the lack thereof. And yeah, well, finally, varying path selection per user, or whatever you do where the user's ID or location influences the path selection, might be a bad idea against many adversaries because it makes them distinguishable. Same for the recipients on the other side. And I think that's about it. Thank you for what I hope is attention and questions.